Welcome to this lesson on linear classification. In this course, we're going to break down one of the most fundamental ideas in machine learning. Linear classification is a simple and powerful method that teaches a model to separate data into categories using a straight decision boundary. You'll see how it works, why it's useful, and where it fits in the broader landscape of machine learning. We'll start with the core concepts, look at real examples, and then move step by step through the model's equation, its strengths, its limitations, and finally a hands-on implementation using a real data set. The goal is to make everything as intuitive as possible, so by the end of this lesson, you'll have a clear understanding of how linear classification learns from data and how it can be applied in practice.
Classification is a supervised machine learning task where we teach a model to sort information into categories. The idea is simple. We give the model examples and their correct labels, and it learns how to recognize the patterns that separate one category from another. A good way to understand this is through real examples. First, consider email spam detection. The model analyzes the content of an email and decides whether it belongs to the spam category or the non-spam category. Another example is heart disease prediction. By looking at clinical features such as age, blood pressure, or test results, the model can predict whether a patient is likely to have heart disease or not. Finally, think about image classification, like identifying cats and dogs. The model learns the visual characteristics that distinguish the two and uses them to make the right prediction. These examples show how classification helps transform raw data into meaningful decisions across different fields.
Linear classification works by learning a straight boundary that separates different groups of data. Each data point has features such as height and weight or pixel values in an image. The model uses these features to place a line or a hyperplane in higher dimensions that best separates the classes. Once the boundary is learned, any new point can be classified simply by checking which side of the boundary it falls on. This makes linear classification fast, simple to interpret, and very effective when the data is roughly separable.
The model relies on a linear equation to create the decision boundary. This equation combines the input features with parameters called weights and adds a bias term. The result tells us on which side of the boundary the point is located. The weights control how steep or flat the boundary is. The bias shifts the line to find the best position. During training, the model adjusts these values until the boundary separates the classes as accurately as possible.
Linear classification offers several important advantages. It trains quickly and makes predictions with very low computational cost. The decision boundary is easy to understand, which makes the model transparent and suitable for teaching, medical applications, or any context where explanations matter. It performs well even when the number of features is large, and it often serves as a solid reference model before exploring more advanced approaches. These strengths make linear classification a reliable starting point for many machine learning problems. Linear classification has important limitations to keep in mind. Because it relies on a straight decision boundary, it cannot capture complex or non-linear relationships in the data. It also struggles when the classes overlap too much, and it is sensitive to outliers that can shift the boundary in the wrong direction. The performance depends on the quality of the features, and in many cases, a richer representation is needed to obtain good results. These limits explain why more advanced models are often required for complicated real-world problems.
All right, now that we understand the intuition behind linear classification, it's time to bring everything to life with actual code. In this notebook, we're going to explore how linear classification works using a real data set. Our goal is to predict whether a user will purchase a product based on their gender, age, and estimated salary. This type of problem appears everywhere, from marketing to healthcare, and it's a perfect starting point to understand how a classifier makes decisions in the real world. We'll walk step by step through the entire workflow. We'll load and clean the data, prepare the features, train a linear model, and finally evaluate how well it separates the two groups. By the end of this coding walkthrough, you'll see how a linear classifier learns patterns from input data and how its decision boundary can be visualized, interpreted, and used to make predictions. So let's jump into the code and get started. Here, we start by importing everything we need for our project. We use train test split to split the data and standard scaler to scale our features. Logistic regression is the linear model we'll train. We import accuracy and other metrics to evaluate the model's performance. Matplotlib will help us plot results, and pandas and numpy are used to handle and process the data. With these tools ready, we can move on to the next step. First, we load our real dataset using pandas.readcsv. This file contains information about users and whether they purchased a product. When we check the columns, we can see the features we'll be working with: user ID, gender, age, and estimated salary. This confirms that our data has loaded correctly and we can start preparing it for modeling. Here, we keep only the columns we actually need for our model: gender, age, and estimated salary, and the target variable, purchased. Then we display the first few rows to quickly inspect the data and make sure everything looks correct before moving on. Next, we check for any missing values using drop_NA. Since we didn't assign it back to the data frame, this line simply verifies whether any rows would be removed. Then we display the first few rows again to confirm that the dataset is clean and ready for pre-processing. Since machine learning models work with numbers, we convert the gender column into numeric values: 1 for male and 0 for female. This prepares the feature for our model. Now we separate our features from the target variable. Gender, age, and estimated salary will be our inputs, and purchased is what we want to predict. Then we split the data into training and testing sets, keeping 20% aside for evaluation. This ensures we can test the model on data it hasn't seen before. Next, we scale our features using standard scaler. We fit the scaler on the training data and transform it, then apply the same transformation to the test set. This puts all features on the same scale and helps the model learn more effectively. Now we create our linear classifier using logistic regression. We fit the model on the scaled training data so it can learn the patterns that separate buyers from non-buyers. Once the model is trained, we use it to make predictions on the test set. Then we evaluate its performance by calculating accuracy, displaying the confusion matrix, and printing a full classification report. These metrics show how well our linear classifier can distinguish between buyers and non-buyers. Finally, let's visualize the decision boundary of our linear classifier. We select two features, age and estimated salary, and train a new model using just these two. Then we create a grid of points across the feature space and use the model to predict the class for each point. By plotting this as a contour along with the training points, we can clearly see how the linear classifier separates buyers from non-buyers. This gives a visual intuition of how the model makes decisions.